That will be you.
Yes, hi, sorry. We have 6 SRC finalists, and so we will have the pleasure of hearing lightning talks from each of them. These talks will be 3 to 5 minutes. Each slot is going to be 5 minutes. So we'll probably have time for 1 or maybe 2 questions. And as people are asking questions, we'll have the next SRC participant come and set up so we can start on time. And if you give us a moment to establish an order very quickly, we'll get right to it.
Hello, yeah. Nice to meet you.
Yeah.
So. This is hard.
Do you want a time warning?
Sure. Yeah. 5 minutes, right?
Five, like the high end.
Yeah. Could I have a warning at 30 seconds, or is that
30 seconds from 5 minutes?
Yeah. Sure,
we can do that.
Okay.
We're gonna.
And how do I stream to the right?
So HDMI.
HDMI, yeah.
Yes.
Sorry, yeah. Give me a sec.
Okay.
Yeah.
Display.
This is. Windows.
Yeah.
Yeah. Multiple displays.
Yes.
That's not working. Advanced display.
Can only
Can you
see the
plug it?
Yeah, I'm gonna try
out
again.
And yeah, maybe you could.
oldest solution in computer science.
Sorry.
Oldest solution in computer science.
Select the display, yeah.
There's only one display.
You don't see it?
Yeah, I don't see it.
Weird.
It should work, right? Just now it worked.
Yeah.
Yeah.
Maybe we can go on with the next person and I can give you my laptop if you want it.
Okay, sure. There's a problem, so we'll go for second and use.
Second
Yeah.
of this. Yeah.
All right.
If you want to share your slides with me, I can.
Sure.
Can you
Yeah.
give me your?
All right.
Yes.
Did I just start?
Our first lightning talk. Our first lightning talk will be from Yang Tzi.
Oh, all right. Thank you. And welcome to my talk. I'm Yong Tzi from the National University of Singapore. My advisor is Prof. Michael Adams. Yesterday, you might have heard my talk on trees. Today, I'll be talking about something different, which are graphs and static analysis and parsing, type checking, automata minimization. What do these problems all have in common, right? Well, these problems all involve self-reference and cycles. And the computational essence to these solutions to such problems are what is known as a work queue algorithm. Work queue algorithms maintain a work queue and repeatedly does some work to give new facts, which we add to a fact database, which then produces new work, and the cycle repeats. When we get to a point where there's no more new work and no more new facts, what we arrive at is a fixed point. Writing work queue algorithms in imperative or functional languages is very hard. For example, this is Dijkstra's graph distances algorithm in Haskell. The problem is that the essence of the algorithm is hidden under lots of boilerplate. Fixed point-oriented programming makes writing work queue algorithms easy peasy. These are languages like Datalog, Datafun, Flix, Souffle, Inca, Flan, and many more. In fixed point-oriented languages, you can write an algorithm for calculating graph distances by solely expressing the essence of the algorithm, essentially by stating what the facts look like and by stating an inference rule for deriving new facts from existing facts. So our contribution is to develop a new fixed point-oriented programming language that compiles to Haskell and has 2 new features. The first is a generalized notion of fact subsumption, and the second is to control evaluation order via rule instance priorities. The intuition is that orders on relations induce subsumption, and orders on rule instances induce evaluation strategies. Some facts subsume others. For example, in Dijkstra's algorithm, if we find that the distance to A is 0, we don't care that finding the distance to A is also 2. We don't care, right? What we want is to care only about the shortest distances. So, in our language, relations are products over partially ordered types. We define partial orders over arguments to relations, such as by saying that a distance of 0 is better than the distance to 7. And the relations in our program automatically inherit that order. Larger facts then subsume smaller facts. For instance, if we already know that the distance to A is 0, and if we later find that the distance to A is also 2, we don't care about the new fact, since actually it doesn't add any new information. It has already been subsumed. Next, some algorithms are optimized by controlling the order of evaluation. For example, Dijkstra's algorithm is optimized by exploring the closest nodes first. What we do is to generate a work queue algorithm that uses a priority queue to store work. What is then retrieved in each iteration is the highest priority work. To control which work is of the highest priority, users can declare a rule instance priority, which are strict partial orders on rule instances. For example, we can write a declaration that prioritizes adding shorter distances first. The result is that these features allow us to faithfully implement algorithms like Dijkstra's algorithm. So to summarize, we have a new fixed point-oriented programming language where orders on relations give rise to fact subsumption, and orders on rule instances give rise to rule instance priorities and evaluation orders. So we have a white paper that describes this in a bit more detail. And lastly, I have a small call to action, which is that we don't have a name for this language. So if you have any ideas, please share some of them with us. Thank you very much.
Might I humbly suggest that to help you in your quest to name the language,
Okay.
We look at the boundary between what your language can do and what it cannot. For instance, what is the space of languages that can be translated into data log, and what still is work that remains to be done, you see. So you look at the limitations, the boundaries. Do you have examples of a program that is still, like that Dijkstra's algorithm?
Yep.
Yeah, but what cannot be done with the existing work?
Yeah. Oh, okay. Cool. Yeah, I think that would be a very good suggestion. Thank you very much. Yeah.
Test. Okay. Yeah, sorry. Yeah.
Introduce yourself just quickly.
Yeah. So hi everyone. My name is Kirill, and today I'm presenting some joint work with Dijkfeng over here, and our advisor is Prof. Michael Adams. And today we're presenting MiniMu, which is a language designed to explore the concepts of duality. So the key starting point of a language is that MiniMu is all about construction and destruction. So we can construct things and destruct them. So you can think of things like algebraic data types and pattern matching. But the trick is that with just this, we argue that we have a Turing-complete language. So how do we do that? So MiniMu is actually based on the mu-mu tilde calculus, something that exposes both expressions and continuations, and more importantly, exposes them in a completely symmetric way, allowing us to have a completely symmetric language. And we'll show why that's important soon. So just to describe what a program looks like in MiniMu, so a program in MiniMu is what we call a command. The command has an expression on the left and a continuation on the right. And a command tells us that this expression will interact with this continuation. And to talk about continuations, first off, we argue that let in our language is nothing more than a continuation. Why is that? Because let expects some expression and continues with its body next, which is also a command. So the program steps to a different command, and that's how the program progresses. But because it's a dual language, it tells us that we have the ability to swap both of these things and put them in each other's position. And what we discover is that this allows us to create the let CC abstraction. And the let CC abstraction is dual, right? So if let expected an expression, let CC expects a continuation. So earlier I talked about pattern matching and the like. So pattern matching in Minimu looks really similar. So we have expressions which are data values and we deconstruct them with matching on the continuation side. But again, it's dual, which means that we can have something like a pattern matching expression with some constructed continuation. And this in Minimu is exactly the difference between data and co-data. So data values are something much more understood. We construct values and we destruct them in our continuation. But co-data tells us that I am a value and I will respond in these ways to whatever observations you give me on the continuation side. And just now I talked about Turing complete, and why we argue that it is because functions are nothing more than co-data. And why is a function a co-data? Functions tell us that I am going to take this value that you give me, and I'm going to do something to it, and pass it to some continuation. What is that continuation? It is exactly the continuation that you supply us with. And it's the exact same as it is in normal programming languages, except that now continuations are made explicit. So, cool, nice and all. Let's start the program in this language. So, for example, let's see what a quicksort looks like in our language. And from this, I'm pretty sure something that becomes very apparent is that with just commands, the language is very painful to use, which is why we talk about making Minimu ergonomic, where we supply different syntactic sugar that are more familiar, that's more easy to use, in order to make Minimu fun and nice to use. And one of these syntactic sugar is what we call the cutlet style. So earlier we were talking about the let continuation. So if let x something is a continuation, then let x equals e is supplying that continuation with an expression. It's just a command. Similarly for match, if matching is a continuation, match e is exactly a command. So in this way, we hide the syntax of a command behind something more familiar. And from that example earlier, this is the same example done in cutlet style. And it looks almost like OCaml, but there's a catch. This code is wrong. Why is that? List split and quicksort both expect continuations. But where are we getting those continuations from? So if you see the desugaring of let x, if you see the desugaring of let, we observe that the entire rest of the program is the continuation to list split. And we have let cc. So all we need to do is introduce a let cc to capture that continuation and pass it to the values like so. And because we're dual, again, if we invert everything, we get a perfectly dual program as well. So, in conclusion, Minimu is a language that's fun, that's cool, because it makes things that are meant to be dual, syntactically dual. And we are continuing to explore different ways to make Minimu easier to use and more fun to use. Yeah, thank you.
We have time for one question as we transition.
Have you thought about adding types to the language? And if you did, how are the types going to be like?
That's a good question. So for Minimu specifically, we have decided to keep it untyped for now. But we have explored typing in subsets of the language. So if you think of, for example, expressions and continuations, right? We've realized that types are actually kind of polarized in the language. So in order to have a well-formed command, you must have an expression of, for example, integer plus, which is an integer expression, and a continuation of integer minus, which is an integer continuation. Yeah.
Hi, good afternoon, everyone. Thank you for attending my talk. So I'll be my name is Brian, and my advisor is also Michael. So today I'll be presenting on my work on relating LL traces and LR traces. So it turns out that LR is actually an abstract interpretation of LL. So parsing is a core process in compilers. And so given a grammar and a string as input, you'll try to form a parse tree to see whether the string is in the language of that grammar. But different parsing styles or parsing algorithms explore this tree in different ways. For example, top-down LL will try to expand and predict from the start symbol, while LR tries to shift symbols until it can reduce them into non-terminals. But at the end of the day, they still pass the same parse tree. So why is it that their mechanisms are so different? Well, it turns out that there is a connection between them. So LL abstracts into LR. But you might be thinking, why do we even bother with this? You know, LR is the strongest deterministic parser that we do have. But there are a few caveats with LR. Firstly, it's very difficult to understand. If you've ever looked at the state diagram of an LR parser, it's horrendous. And this also gives rise to bad parse errors. So this will be an example of an LR parse error. It just says like unexpected in, expecting a statement. And this doesn't give the user any context. Even if I were to give the offending line, the user will have to look at it and probably parse it in a top-down manner as humans usually do. It would be much better if you could give them context such as, oh, well, I'm trying to parse this if statement. I expected a statement, but then I found an int. This is much more human readable, and it's something that LL-style parse errors generate. So is there a way that we can, with our work on showing LR as an abstraction of LL, we can get the best of both worlds? We'll be able to use an LR parser and capitalize on its expressive power on grammars and run it until maybe there's some parse error state. And instead of generating the error message from here, we first concretize it into its corresponding LL trace, and from there we can produce much better error reporting as shown previously. So this is my work, which is the universal parsing automaton. And the way that it works is that it's a single stack-based machine where on the stack it contains parsing items. And so this is how the UPA relates to LL and LR. It kind of sits in the middle. It's a nice middle ground between the two. So what are the UPA operations? There are three main core operations. The first one, which is matching. So it basically matches a terminal and advances a bullet for a given item. And if, let's say, it's trying to pass a non-terminal, it will it'll add a new stack item, which is essentially like calling a call frame in a recursive descent. And once it's done passing that, it will return back. So this is actually no more than a recursive descent parser. It's just that we have a more explicit return statement. And with this, it's actually enough to weakly simulate LL. What that means is that every LL operation would have a corresponding UPA operation. So LL's expand corresponds to UPA's call. LL's consume corresponds to UPA's match. But since it's a weak simulation, there are some silent return calls that we need to do to keep LL and UPA in lockstep. But what this means is that every LL trace has a corresponding UPA trace. So from here on, we'll just be reasoning about UPA with respect to LR. So how does the UPA abstract into LR? Because we keep the stack of items, we are able to construct the viable prefix of the UPA configuration. And this viable prefix is essentially the symbols that sit on the stack of an LR parser. And from there, we can feed the symbols into the goto function of the LR parser and reproduce the corresponding LR configuration. So now that we are able to abstract multiple UPA configurations into one LR configuration, what about the reverse? We're able to do the same thing, but this one will be a bit more of an exhaustive search. So what it means is that every LR shift will correspond to a partial trace of the UPA. So it could be multiple calls followed by a match of A, and the LR's reduce of some production will be simply the return of the UPA. So what does this mean? This just means that multiple LL traces abstract into a single LR trace, and a single LR trace can be concretized into multiple LL traces. So thank you. That's the end of my talk.
We have time for one really quick question while we transition. Have you implemented this? Like
not yet. So
yet.
like what we have right now is the theoretical foundations, but the next step will be to implement a working version.
Cool.
So, hi everyone. My name is Zhiqi Chen from Institute of here. Thank you. My name is Zhiqi Chen from Institute of Science Tokyo. Today, I'd like to share with you my work on live FFO programming with titles. The motivation of our work can come from the increasing popularity of effect handlers in programming languages. They can uniformly express many computational effects such as exceptions, mutable states, and non-determinism. However, for beginners, effect handlers can sometimes difficult to understand and implement. Take state effect as an example. A beginner may easily get lost in the lambdas and continuations and wondering what the continuation k is and what the variable v and f represent. We aim to provide a better learning experience for beginners of effect handlers. To achieve this goal, we combine effect handlers with the notion of typos. Typos is a mechanism to type check and run incomplete programs. And it is available in languages such as Hazel and Agda. By incorporating this mechanism into FFO languages, we can, for instance, run an incomplete handler and see what the value of the variable and the content of the continuation are. And so far, we have formalized a calculus of effect handlers and typos by extending the core calculus of Hazel. And it is based on gradual typing, and we added an effect tracking facility found in standard effect handler calculi. And in addition to the formalization, we also built a prototype implementation in Haskell. It shows the correct result with whole context, which means that our semantics works just as we expect. However, the result is quite verbose because the continuation is not being reduced in the current implementation. So in future work, we will build a new formalization and implementation based on a constraint-solving-based approach. This switching is because gradual typing doesn't give us the strong normalization property, and which is essential to make the evaluation safe at the presence of both effect and host. And also, we want to make the output more readable by allowing a full normalization, and we can reduce the continuation body. And finally, we aim to prove the type and effect safety in our language. In summary, we propose to make effect handlers more accessible through typos. Thank you very much for listening.
I'll time myself. Yeah. Oh, there we go. So hello, my name is Bryson Finkston. My advisor is Jason Heeman. And today I'll be talking to you about visualizing logic programming search with fine-grained small sub-semantics. So I'm going to assume some basic familiarity with logic programming. Specifically, if you know some Prolog, this should come somewhat naturally. So here we have two programs, one in Prolog, one in Minikanren, and they both express the same solution set, but what's different is the way they enumerate their answers. So Prolog, which uses a depth-first search, enumerates its answers in the order that they're in. So this is very natural and easy to reason about. However, Minikanren enumerates answers in a seemingly random way. So we start with the last one we wrote, then we go to the first, and then we do some stuff in the middle. So understanding this behavior is key to understanding your programs in Minikanren. And staring at the program for a really long time won't tell you the answer because the search is implicit within the implementation. So one way you might try to go about understanding this is with small sub-semantics. So that's exactly what we did. We created small sub-semantics for Minikanren. For the sake of time, we can't go through all of these right now, or any of them, I guess. But if you want to learn more about this, I'll be talking at the Minikanren workshop on Friday. But to understand the semantics at a high level, we're basically, you treat your program as a tree, and your reductions are just tree reductions. So you're stepping from a search tree to a search tree. So your program consists of goals and states, disjunctions, conjunctions, and some control operations. And your values are either failure or a stream of answers, which is basically a linked list, which is a tree. Oh, sorry. So that's the semantics. We mechanize them in PLT Redux, and so we implement them in PLT Redux so we get that mechanization for free. We also get some things like you can define judgment, so we define what a well-formed program looks like, and then we could verify some properties of our semantics, such as the reductions are deterministic, so we only step to at most one tree, and they preserve their sound semantics as well. So you'll never go from a well-formed program to a non-well-formed program. So this is the visualizer UI. On the left-hand side here is where you would input your program. So this is the program we saw on the first slide. And so you input your program, and it's just the standard core Minikanren language, and you can load up your program. And there's some nice quality of life features. So you'll see at the top, there's the step count and the name of the step. So if we keep stepping, our first step, we substitute our fresh variables from our query. Some other nice things are that you can click on a node, and that will highlight in your source where that goal came from, and you can do that the other way around. So if we click on this unification here, we'll see it corresponds to that goal in the tree. And so there's so you can step through your program, and you'll see it's just reducing certain subtrees. One last thing that's pretty nice, and so this is showing the interleaving behavior. Well, you can also inspect the state of your goals as you're stepping. So you can see here that this goal has a state with a substitution mapping that logic variable to the fish. So, yeah. So that's it. If you want to see the source code, that's on the left. If you want to try out the visualizer, that's on the right. Thank you.
Because we're over time, let's take questions offline.
All right. So my topic was on optimal effects via token passing, which basically, so my entire work basically comes down to like having ordered execution in parallel to unordered reduction. And execution is like something that has side effects, like I/O or something, and reduction is entirely pure. And unordered in this case means that you could then, after like having this theoretical construct, decide whether you maybe want to use something like an optimal reduction scheme or maybe even reduce it in parallel, and that's then up to you. But first let's get down, like this is done via token passing, but the first important part is how this even, like what is optimality, because actually my topic is like optimal side effects, right? So basically optimality is you combine call by need, which is a lazy evaluation strategy, with radix sharing. And then you achieve something like maximal laziness. So for example, if you have this function which takes an x and then adds some big number or something, some algorithm, then this would be evaluated twice in something like call by need in Haskell, but in something like optimal reduction strategies, this will only be evaluated once. So, and how you achieve this kind of optimality, this optimal reduction, is via interaction nets. And this is basically a graph encoding of your program, which is then reduced until you achieve some normal form. And specifically in my work, I extended this interaction net with side effects. So if you actually like write a program and translate it to this graph, it will look somewhat like this, like some huge graph. And then everything that is red can then be reduced. And actually the order does not matter, because interaction nets are like inherently unordered. And then if you want to encode a certain structure, like because side effects are supposed to be evaluated in a certain order, you have to use a different strategy. And this is where the main idea of my work comes in, which is basically that we have tokens in this network, and these tokens traverse the net in a specific order and execute all actors. And actors are these, or this is first what tokens are, because these tokens move through the net. And once they hit an actor, which is this quickly thing, it causes a side effect. And this side effect will then be somewhat like if you have a side effect called, or an action called read, then the side effect will be that something from the console is read in, like a number 42, and then the side effect happens. And then the token, which is like this blue arrow, will return as a code token, which is the red arrow. And then it will continue traversing the graph. And you can also do some different things. For example, you could say, yes, a token basically resembles a thread because every execution of an action requires a token. So if you remove this token, then you basically abort this thread. And if you have multiple tokens, you would have multiple threads in your network that you evaluated. And you can also do different things with these. For example, you could like load different networks into your network. For example, that's how I implement recursion in my implementation, because then you can basically have as a side effect something like a foreign function interface or remote procedure calls, and then load these as a side effect into your network. And the important part is that you still have this reduction, which is pure, as I said in the beginning. And in this case, for example, you have a beta reduction. I know you may not be comfortable with this layout yet, but this resembles beta reduction. You have to trust me here. And this token is at the bottom right. And this token can only continue after beta reduction happened. So basically the reduction, the pure reduction, paves the path for the execution, which then has side effects. And how these tokens are then directed is specified by graph rewrite rules. And for example, I have like researched many different redirection rules. But for example, you could implement something like a monadic style, which looks a bit dangerous, I know. But basically, you have this rules which state how this token will be redirected if it is at certain points in your graph. And then you can also do something like a direct call by value style, and you can do a lot of things. But all of this happens while you still have a one-step diamond property, which means that you can reduce it in any order, like you can reduce this network in any order, still have the correct execution order, and still can do something like parallelism without changing the eventual reduction steps. And then you could also have multiple tokens with some kind of fork, or you can have some join operation for threading and racing, and then you can, this is what a race would look like. But this is basically all I did. So you have like ordered token traversal happens in parallel to the unordered graph reduction. And the optimality results, or the optimality property of interaction nets and strong confluence, which is needed for parallelism, remains. And now I did a lot more in my thesis, actually, which is like proofs, type system, asynchronous partial application, and I also implemented a core calculus, so you do not need these graphs. And then I also have a lot of results, but you can find this here. Thank you.
Thank you. You have a question?
Can I suggest as a way of structuring your results that in the existing literature on interaction nets, they actually work with the pure untyped calculus. Now, you immediately jumped into effectful actions. Perhaps an intermediate step is if you introduce constants and primitives, right, before you actually get into full-blown, this is a node representing a foreign function call.
Yes, yes. I mean, I also have some operators, like built-in operators, but yeah, there's also not that much time. So yeah. All right.
Thank you. Thank you for your attention. We will announce the winners of the student research competition at the business meeting later this afternoon.